Hello everyone, I'm Hari. I'm here to present our work on global guidance for local generalization in model checking. This is joint work with Yuting Chen, Sharon Schwam, and Eric Finkel. So let's get started. We are primarily interested in proving the safety of infinite state systems. Our algorithm works on all systems that can be expressed as nonlinear constraint Horn clauses. However, to keep things simple, we are going to explain everything relative to sequential programs with a single loop. In this context, safety can be established by generating inductive loop invariants. We are particularly interested in IC3 style model checking algorithms. These algorithms generate predecessors to bad states called proof obligations and block them and generalize to learn lemmas. These algorithms do this repeatedly until they generate an inductive invariant. The example on the right is an example sequential program. It has two variables, a and b, both of which are unbounded integers. Inside a while loop that runs arbitrarily many times, both variables are incremented. Once the while loop exits, it is asserted that if a is less than 5, so is b. An example of a proof obligation can be a set of states where a is between 0 and 4 and b is equal to 4. This proof obligation can be blocked using lemmas like a equal to b or a plus b less than 4. So one critical aspect of such IC3 style model checking algorithms is local reasoning. That is, they generalize from single proof obligations. This generalization is typically done using interpolation, and interpolation can be quite magical. For example, interpolation can generate terms like a equal to b even though this term did not appear anywhere in the proof obligation or in the transition system. However, local reasoning has its problems. It is not aware of the structure of the inductive proof constructed so far. Interpolants are a sole function of the heuristics inside the underlying SMT solver. Therefore, as far as an interpolation algorithm is concerned, the lemma a plus b less than 4 is just as good as the lemma a equal to b. However, from a model checking perspective, for this particular program and for this particular property, the lemma a equal to b is better than the lemma a plus b less than 4. However, given a different program or a different property, it could be the case that the lemma a plus b less than 4 is better than the lemma a equal to b. The point here is that it is impossible for the interpolation algorithm to understand which lemma to learn in which context. So this problem is much more crucial in infinite state systems than in finite state systems, because it is very well possible that in an infinite state system, you learn multiple bad lemmas and you diverge. However, in a finite state system, since there are only a finite number of interpolants to choose from, you will eventually converge. So in the paper, we describe 3 different problems with local reasoning. These are myopic generalization, excessive generalization, and getting stuck in a rut. In this talk, we will explain what myopic generalization is. Please read the paper to understand the other 2 problems with local reasoning. Now, there is a nice little comic here. Please read the paper and get back to the slide to understand the comic better. We demonstrate myopic generalization using an example program. This program has 4 variables, a, b, c, and d. All of them are unbounded integers, and all of them are incremented inside a while loop that runs an arbitrary number of times. In each iteration, either both a and b are incremented or c and d are incremented. Finally, it is asserted that if a is less than c, then b is less than d. To see myopic generalization, let's take Gspacer, a state-of-the-art IC3 style model checking algorithm, and run it on this example. If you run it in the first iteration, Spacer learns the lemma a minus c less than 0 implies b minus d less than 0. This is in fact the property that we want to prove. However, Spacer has not proven that this is inductive. Therefore, we continue. In the next iteration, Spacer learns two lemmas. A minus c less than 1 implies b minus d less than 1, and the same lemma but with a constant minus 1. What is going on here? Well, Spacer actually splits on the if then else branch. To learn one lemma, it follows the then branch. To learn the other lemma, it follows the else branch. Okay. Now, as Spacer progresses, it learns more and more lemmas which are very similar to the previous lemmas that it learned. We all see where this is going. Each of these lemmas are good enough to block single proof obligations, but none of them are good enough to learn to be an inductive invariant. So even though Spacer learns many similar lemmas, Spacer does not figure out that it's not making progress. This is what we mean when we say that local reasoning is myopic. So how do we solve this problem? Well, we introduce global guidance. Okay. So this is Spacer. It has two main data structures, a proof obligation queue and a lemma trace. In each iteration, Spacer queries a proof obligation queue for a proof obligation alpha. It queries a lemma trace for a frame OI. It tries to block alpha. If it's not successful, it generates a new proof obligation, alpha dash, and if it is successful in blocking alpha, it learns a new lemma L. This is where global guidance kicks in. When Spacer is about to learn a new lemma, we take a global view of the proof by querying a subset curly L of lemmas from some frame OK and taking a proof obligation phi, and then we guide Spacer by learning a new lemma psi and adding it to the lemma trace, or generating a new proof obligation gamma and adding it to the proof obligation q. We introduce three rules, subsume, concretize, and conjecture, to achieve global guidance. In the rest of the talk, I will explain these three rules. The first rule is the subsume rule. It says that if you have a bunch of lemmas curly L such that you can generate a new lemma psi that subsumes each of the lemmas in your subset, then you can add psi to the trace. Just to get an idea, imagine that Spacer learns two green lemmas in some context, and after a few iterations, Spacer learns two more green lemmas. Now, what's Spacer trying to do here? Spacer is trying to represent a set of an over approximation of reachable states using a set of lemmas. If we apply the subsume rule, we can represent the same set of the same set of over approximation of reachable states using a single lemma psi. What is the advantage of learning a single lemma? Well, it can be it is much easier to generalize the single lemma than to learn infinitely more green lemmas. To make things more concrete, I will explain the subsume rule on the running example we had. Recall that earlier Spacer diverged by learning lemmas of the form a minus c less than 1 implies b minus d less than 1, and with different constants instead of 1. In order to compute a subsume lemma, we first go into the cube space, which is the negation of lemma. Now we can see that each of these are now conjunctions rather than implications. The nice thing about this is that these are polytopes. We can apply a convex closure algorithm to compute the convex closure of these three shapes. In fact, we can make certain assumptions so that computation of convex closure is simplified. Please read the paper for the assumptions that we make and the new algorithm that we get for computing convex closure. So let's say we do compute the convex closure. It is going to be this red region. It has three literals. First is the nice literal a minus c less than b minus d, and the other two literals are boundary conditions. These two boundary conditions can be dropped by using inductive generalization. Now, if we transform this cube into a lemma by taking its negation, we can see that we can actually get an inductive invariant for our running sample. Okay, so that's all about the subsume rule. Now I'm going to explain the second rule, which is concretize. I'm not going to explain the formula here, I'm just going to explain it pictorially. Imagine that you have a proof obligation, which is a yellow circle, and it's difficult to block that using a single lemma. In this case, we can use concretize rule to divide and conquer this proof obligation. On application of the concretize rule, you get an under approximation gamma of the yellow region, and you can ask spacer to block this under approximation. Once spacer blocks this under approximation, it will learn a new lemma, which is the blue zone here. This new lemma will definitely block the under approximation, but it need not block the original proof obligation that we started off with. So we can apply the concretize rule again to divide the proof obligation again and block it to learn a new lemma. The hope here is that when we do it enough times, we can generate a number of lemmas which can be put together and generalized to block the whole proof obligation. In the paper, we explain in detail what exactly we mean by terms like partially blocks and how to under approximate a proof obligation for the theory of linear integer arithmetic. Please read the paper for such details. Now, the third and the final rule for global guidance is the conjecture rule. It is applicable when the proof obligation 5 has two regions, the violet alpha region and the yellow beta region. And there are a bunch of lemmas, bunch of green lemmas that block only one part of the proof obligation. In this case, all these lemmas block the yellow beta part of the proof obligation, but none of them block the violet alpha part. So the conjecture rule allows spacer to abstract this proof obligation to get an over approximation, which is the alpha region. Now, if we add alpha to the proof obligation Q and block it and generalize, maybe we will get a nice blue region, which might be an inductive invariant. Again, we go into much more detail about when the conjecture rule is applicable and how to construct the alpha region from the proof obligation. Please read the paper for those details. Okay, so far we have seen global guidance. Global guidance is achieved using three rules: the subsume rule, which adds a new lemma psi to the lemma trace; the conjecture rule and the concretize rule, which generate a new proof obligation gamma and adds it to the proof obligation Q. There is the conjecture and the concretize rules are complements of each other in the sense that conjecture rule over approximates a proof obligation, whereas the concretize rule under approximates it. Okay, so we implement these three rules on top of spacer, and we call the new solver Gspacer. We evaluate Gspacer on linear integer arithmetic instances from the CHC competition. And we can see that, in fact, Gspacer solves almost 20% more instances than spacer. But more interestingly, Gspacer is stable even without interpolation. That is, even if we turn off interpolation, Gspacer does not lose performance. Whereas in the case of spacer, turning off interpolation leads to a decrease in performance. Gspacer also participated in the latest edition of the CHC competition, and it won 3 of the 4 tracks. The second part of our evaluation compares Gspacer with linear arbitrary. This is a data-driven, machine learning-based invariant inference algorithm presented at PLDI 18. And it stood out because its evaluation showed that it outperformed spacer on a curated subset of benchmark instances from SVComp. We tried to compare a Gspacer with linear arbitrary, but could not compare it on the CHC competition instances because linear arbitrary was pretty poor. In fact, it was much poorer than Spacer on those instances. So we compared linear arbitrary with Gspacer on the benchmark instances from the PLDI 18 paper. We first replicate their results. That is, we can see that Spacer solves much fewer instances than linear arbitrary. However, we find that Gspacer solves more instances than linear arbitrary. So to conclude, we present a global guidance technique to mitigate limitations of local reasoning. We find that the global guidance technique is stable under different interpolation strategies. In fact, it is stable even if interpolation is turned off. Finally, we conclude that adding global guidance to model checking algorithms is very effective. In fact, it is more effective than invariant inference algorithms like linear arbitrary and local reasoning based model checking algorithms like Spacer. As future work, we would like to extend global guidance to other theories, especially theories where there is no interpolation, like bit vectors or arrays. We would also like to add more rules. Specifically, we believe that global guidance can help symmetry breaking while verifying distributed protocols. Thank you for listening.